In order to tune the transformer, we firstly have to know the problem, why we don't get as much current as we need. So on the primary side we have 230 volts, because I live in Europe. On the secondary side we have 2000 volts from the transformer. The measured resistance on the secondary side is RL2, which equals to 153 ohms. The frequency is 50 Hertz, and impedance, which is complex to calculate, is 5592 ohms. The effective voltage is 2000 volts, but the voltage we use for our calculations is 2828 volts. To calculate the current now, we just use Ohm's law, which is voltage divided by resistance equals current. So in this case, for the effective current, it's 2000 volts divided by 5592 ohms, which equals 0.357 amps. And with the effective voltage, which is 2828 volts divided by 5592 ohms, it is 0.505 amps. So this is the current we get out of a microwave oven transformer without tuning. As you can see, the impedance or resistance of the secondary side is really high, with around 5.5 kilo ohms. So we can't expect much current out of that. And in order to get more current, we have to reduce that resistance. We can do that with an LC circuit. So we add a capacitor to the circuit. With a capacitor, the circuit now looks like this. So this is our secondary side and our primary. This is one capacitor or three in parallel, which equals to one big capacitance. So if we just use microwave oven capacitors, which are around about 2000 volts AC with 1 microfarad, we have 3 microfarads in the end. In order to calculate our new impedance, we need to inductivity of the secondary side. We can guess that the primary side has an inductivity of around about 1 microhenry, which we can see here. This guess is an educated guess, so it's not 100% accurate, but it's a good starting point for our calculations. In order to calculate the inductivity of the secondary side, we have to divide the number of turns on the secondary side by the number of turns on the primary side in this formula here. And if we put all the numbers into it, we have around 2000 windings on the secondary side and 230 on the primary. We get an inductivity of 75.6 microhenry. The resistance of L2 stays the same because we're not adding any load to it. This is still 153.91 ohms. The frequency also stays the same, but now the new number we have is the capacitance, which is 3 microfarad. So this is the formula to calculate the impedance of the secondary side. We firstly have to calculate XL and XC. For XL, the formula is 2 times P times frequency times inductance of the secondary side. If we put the numbers in, we have 2 times 2P times 50 Hertz times 75.6 microhenry. If we want to put that into our calculator, we have to type 75.6 times 10 minus 3, because microhenry. That is equivalent to 23.75, and for XC it's 1 divided by 2P equals 2P times frequency times capacitance. So if we put the numbers in, it's 1 divided by 2P times 50 times 3 UF. For microfarad or UF, it's times 10 minus 6, and it equals to 1061.72 ohms. If we now put the numbers into the impedance formula, which we have here, So if we put the resistance of 153.91 ohms in plus 23.75 minus 1061.12, we get an impedance of 1061 ohms. So as you can see, it's way smaller than the impedance we had for the old circuit without a capacitor, which was 5592 ohms. So if we now calculate the current of that, we get a current of 2.66 amps. Now we could theoretically increase the capacitance even more to get even higher currents. With 5 capacitors or 5 microfarads, we get a current of a way higher current, around about 5 amps, but that would be way too much for the secondary side and also for the primary side, because it would be way over the 3600 watt limit that a normal 230 volt circuit can deliver. So there are two options that could happen. Firstly, the transformer could burn out, and secondly, the breaker could pop. So none of those scenarios are good. So we just should stay around 2 to 3 capacitors, maybe even 4, but that would already push the limits of most circuits. So this is how I wired my 3 capacitors for my circuit. We have 3 microwave oven capacitors, which are wired in parallel. So each of those pins are connected to each other for the side. And we have 2 new terminals. So those are the wires that we connect to the electrodes at the end. So this goes to the electrode and this goes to the transformer. This is now without resonance capacitors, as we're looking at the 0.3 amps with the 5.5K resistance. So not too bad, but not what we want. So this is now with 3 resonance capacitors, as shown in the calculations. So we should get around 3.5 amps of current on the secondary side. Let's see how that looks. So as you can see, we get way bigger. So as you can see, we get way bigger arcs with the higher current. So this was now approximately 3.5 amps of current at 2000 volts. As you can see, the arcs were more than double the size as before. So the resonating capacitors definitely made a big difference on the circuit. That's quite cheaply to do. You can buy around 1 capacitor for, let's say, €5 or so. If you want to do it that way, or just buy used microwaves for like €10 or something around that.